Hello, today we're going to talk about atomic structure. I just kind of give a general introduction to atomic structure. So to briefly go over what an atom is, it's the simplest form of matter. That we can break apart into using chemical means. And we had this idea that atoms were just kind of a small sphere that made up all of the different substances on Earth. But then eventually we found out more and more about the atom as we developed more advanced technology. Like we understood that there were positive charges in the atom. And then we had this idea that those positive charges were concentrated in the center and that atoms were mostly empty space. And then we had this idea that around the outside of those positive charges, the electrons are moving around in these orbits called energy levels. And so our view of the atom got more and more detailed as we have more and more information using advanced technology. So let's talk some more about the nucleus, which consists of protons and neutrons. The nucleus was discovered by Rutherford, and he used this gold foil experiment where he shot alpha particles at an atom, and then some of them bounced back, but many of them passed through. So we've got our generic atom here, and in the very center, you have a very small, dense, positively charged nucleus. So the nucleus is that center portion of the atom, and it consists of protons, which are positive, and neutrons, which are neutral. Now, it was easy for us to detect protons to begin with because they're positively charged. Neutrons, I'm going to use as just a circle for neutrons. Neutrons were harder to detect because of their neutral charge, but they help to balance the stability of the nucleus. So again, this nucleus is this small, dense, central portion of the atom. It consists of protons and neutrons. Protons are positively charged subatomic particles, and neutrons are neutral subatomic particles. All right, so we've got our atom with our positively charged nucleus because of those protons, and there's neutral neutrons. But atoms are electrically neutral overall. So the protons that are positive have to be canceled out by something that is negative, and those are the electrons. So because I drew 4 positively charged protons, there should be 4 electrons. So we've got protons, neutrons, and electrons. And those are our 3 subatomic particles that are in the atom. And protons are positively charged, neutrons are neutral, and electrons are negative. Protons and neutrons make up the nucleus, and electrons are around the outside. Protons and neutrons also contribute the most mass. Electrons have a mass, but it is very, very small. So teeny tiny mass, very, very small particles, and they're moving very quickly around the atom. Which is why if you were to repeat Rutherford's experiment and shoot particles at an atom, most of those particles would pass straight through, but occasionally when they bump into the nucleus, they could bounce back. And so that's our general view of the atom that you should definitely know. Protons, neutrons in the nucleus, positively charged protons, neutral neutrons. They contribute most of the mass of the atom. The atom is mostly empty space. Electrons take up most of the volume, but they have teeny tiny mass and they're negatively charged. A couple things I want to point out when we're talking about the forces of things going on in an atom. When we have our positive protons and our neutral neutrons in the nucleus, protons are all positive, so they want to repel each other. Because they're of like charge. They want to repel each other. There's something called the strong nuclear force holding the nucleus together, which helps bind those neutrons and protons, and the neutrons help to stabilize that and kind of overcome some of those repulsive forces from the like charges. The electrons are around the outside. The electrons also want to repel each other, but then the protons and electrons will attract one another because they're opposite charges. So opposite charges attract, like charges repel each other. Now, atoms are identified by their number of protons. So we say like all atoms that have 1 proton are the same type of atom. All atoms that have 6 protons are the same type of atom. All atoms that have 82 protons are the same type of atom. So the identity of an atom is given by its number of protons. And we call that number of protons the atomic number. All right? And we assign names to them because it's simpler for us to reference them by a name than just a number. So all atoms that have 1 proton are called hydrogen atoms. But we could just call it 1, right? Because they all have 1 proton. All atoms that have 6 protons are carbon atoms, and so forth. So we use that atomic number, which is the number of protons, to identify the atom. Now we can also have isotopes of atoms. Isotopes have the same number of protons, so they have the same identity, but they have a different number of neutrons. So let's say you've got 6 protons and 6 neutrons in one atom. And in another atom, I have 6 protons and 7 neutrons. These would be isotopes of each other. They're the same type of atom. They both have 6 protons, but they have different numbers of neutrons, so they are isotopes. They are structurally different, but they have the same type of atom. Now, the mass number is how we can kind of figure out which one's which. The mass number is the total of protons and neutrons. Protons plus neutrons gives us the mass number. So if you have 6 protons, 6 neutrons, our mass number is 12. If I have 6 protons and 7 neutrons, my mass number is 13. So isotopes have the same atomic number because they have the same number of protons, but they have different mass numbers because the mass number is protons plus neutrons, and neutrons are different. Now, when we're dealing with isotopes, we use something called hyphen notation. So I was giving you some different isotopes of carbon. We write the name of the element and then a hyphen and then the mass number after that. So you'll see carbon 12. I also showed you carbon 13 because that was the other mass number I showed you. You might have heard also of carbon 14, which is used for carbon dating. So the mass number comes after a hyphen mass number, and that's the total number of protons and neutrons. We can also use something called a nuclear symbol. The nuclear symbol has the symbol of the element, which is either 1 letter or 2 letters, and the atomic number goes in the bottom left. So for carbon, that's 6. It's always 6 for carbon because it's got 6 protons. The mass number goes in the top left. And then if there is a charge, it goes in the top right. And we'll talk about more about charge later on. So far we've only dealt with neutral atoms. So there's no charge. So nothing would be written in that top right corner. So this would be for carbon 12. I could have carbon 13, and I could have carbon 14. Now sometimes people omit that bottom number because C tells us that there are 6 protons. But if we're writing the full nuclear symbol, then you should include all of the numbers. All right, so let's talk about ions. All of the atoms we've discussed so far have been electrically neutral, where the protons and electrons are the same. But you have ions that exist. Ions are not neutral because the protons are not equal to the number of electrons. All right, and so a cation happens when an atom loses electrons, and an anion happens when an atom gains electrons. And so if you're losing a negatively charged electron, it becomes positively charged overall. So if you get rid of a negative charge, it becomes positive. Anions, because you're gaining electrons, you're getting more negative charges, so it has a negative charge overall. And the way that I remember that is cations have this plus sign in the middle. It's a T, but it looks like a plus sign. And so you can remember cations are positive and anions are negative. So these ones are not neutral atoms. They are ions because their protons and electrons are not equal. Let me give you an example. If I have my normal carbon atom, which looks like this, I know this one has 6 protons because carbon always has 6 protons. And because the mass number is 12 and there are 6 protons, I know that there's 6 neutrons because they have to add up to the mass number of 12. Right? And because there's no charge, it's electrically neutral, I know there must also be 6 electrons because those two have to balance each other out. The positives and negatives balance. Now let's say, for example, I form an ion. And let's say I make a, let's just say it makes a 2 plus ion. Okay, so it's a positive charge, it's a cation. Okay. It must have lost electrons. It has a positive charge, so it must have 2 more protons than electrons. But our protons don't change. We always have 6 protons. That's what makes it carbon. Our neutrons also haven't changed because the mass number is still the same. So it lost 2 electrons. It must have 4 electrons to give it that positive 2 charge. Now, let's do one more example. If I have, this time I have a, let's say it's a negative 3 charge. Okay, I still have 6 protons because it's still carbon. My mass number is the same, so I still have 6 neutrons. But now it's a negative 3 charge. In order to be negative, it must have gained electrons. And it must have gained 3 electrons from neutral. So this one would have 9 electrons. Because there's 3 more electrons than protons, that gives it that negative 3 charge. Okay, let's do a couple examples here. This first one I have nitrogen 14. Nitrogen always has 7 protons because its atomic number is 7. You can use a periodic table to look that up. It always has 7. Now the mass number is 14. So that means the protons and neutrons added together gives us the mass number. So there must be 7 neutrons here. 7 plus 7 is 14. Also, because there's no charge written, I know that it must be electrically neutral. The protons and the electrons together determine the charge. And because there's no charge, I know they must be equal. Let's do another one. Oxygen always has 8 protons. Okay. There's no mass number written on the top here. So what I do is you can use the periodic table and you can round the mass from the periodic table to the nearest whole number. And so the mass in the periodic table rounds to 16. All right. So again, if there's no mass number given, you can round the mass from the periodic table to the nearest whole number. And so 8 plus 8 gives us 16. So that's how we can get the neutrons. Now in this one, I have a charge. There's a negative 2 charge. I must have 2 more electrons than protons. So 10 electrons there because there's 2 more electrons than protons to give that negative 2 charge. Our next example is aluminum. Aluminum is number 13. Okay. And the mass number is 29. Something plus 13 will give us 29. And so you can subtract and you will get 16 there to get the number of neutrons. Because this one has a charge, charge is plus 3, I must have 3 more protons than electrons. So this one will have 10 electrons to give us that positive 3 charge overall. Now our last example here, chlorine. Chlorine 37. Chlorine always has 17 protons. And so remember, this is hyphen notation. So that is the mass number, just like we were using before. And so you can subtract the protons to get the neutrons. So 20 in this case. And there's no charge written. There's no positive or negative charge there, so I know that the protons and electrons must be the same. So here's another isotope example. We'll look at chlorine 35 and chlorine 37. Remember, you can also write it like this. Chlorine always has 17 protons. So they both have 17 protons because they're both chlorine. I can subtract the mass number minus the protons to give us the neutrons. And so in this case, I have 18 neutrons. And this one, I have 20 neutrons. And then finally, neither of these have a charge. So the protons must be equal to the electrons for both of them to give us that neutral charge overall. And so you can see that these are isotopes. They have different mass numbers, different neutrons, but everything else is the same. So they're isotopes. Okay, so if you were to look at a periodic table, and let's look at hydrogen, you will see there is the atomic numbers always listed. And then you'll also see usually an atomic mass. Now this number typically has a number of decimal places, and this atomic mass is also called the average atomic mass or atomic weight, and it is a weighted average of all of the isotopes in a naturally occurring sample. So that's why you don't see whole numbers typically for that, because it's an average of the different isotopes. Now, if you remember, I did say if you are not given a mass number, you can typically round that atomic mass to the nearest whole number to estimate the mass number, but they will frequently give you the mass number. Now, this atomic mass is measured in atomic mass units, which is also abbreviated AMU, because it's easier for us to measure that than to use like grams or kilograms, because atoms are so tiny. It would be this crazy small number of grams or kilograms. And so this value on the periodic table is a weighted average of the atomic mass. Now we can actually calculate the average atomic mass for a sample with 3 steps. Our first step is to change the percents to decimals. And we can do this by divide by 100 or move the decimal twice. Move the decimal point twice. Our second step would be to multiply the decimals that you got in step 1 by the mass of the isotope. And our third step, you're going to add all of your products together from step 2. And you follow the same 3 steps every single time. And we'll do a couple examples. So here's our first example. We've got 25% silicon-28 and 75% silicon-29. Our first step is to change the percents to decimals. There's a decimal point at the end of 25. If I move that over 2 places, 25% becomes 0.25. 75%, if you divide by 100 or move the decimal twice, becomes 0.75. That's our first step. Second step, I need to multiply those decimals that I just found by the mass number that's associated with it. So 25% was silicon-28 and 75% was silicon-29. So I want to make sure that they match up. So when I multiply this first one, I get 7. And when I multiply this second one, I get 21.75. My last step, I need to add the products that I found in step 2. So I get 28.75. And our unit is always AMU, atomic mass units. All right, here's another example. Copper consists of 69.15% copper 63, which has this very long mass. and 30.85% copper-65, which has an atomic mass of 64.927794. Now, sometimes we will just use the mass number, but if we have a more specific mass, then we should use those values instead. And so we're going to follow the same 3 steps, though. You're going to change the percents to decimals. So move it over twice, 0.6915. And the other one is 30.85. I'm going to move the decimal twice. Second step, I'm going to multiply by the associated mass. So this one I'm going to multiply by 62.929601. And the 0.3085 I will multiply by 64.927794. When I multiply the first one, I get 43.52. And for the second one, I get 20.03. For our third step, then, you're going to add those 2 products together. And I get 63.55. And that's AMU is my final unit there for my average atomic mass of copper. I just want to wrap up today with a very brief comment about radioactivity and nuclear radiation. I did mention that atoms are the simplest form of matter and the smallest unit that we can break it down using chemical means. Radioactivity is interesting because this is part of what we call nuclear chemistry or nuclear reactions. And these can actually change the type of atom because they can affect the nucleus. So they can change the protons or neutrons or electrons in an atom, whereas chemical reactions can really only affect the electrons. And so radioactivity, you're going to have some kind of decay where there's some emission of particles. And there's different types of radiation, alpha particles, beta particles. For this class, we don't need to know the differences there. But these radioactive elements are not stable. Okay? And so they're going to emit these different particles as they decay into more stable isotopes. And so we call that nuclear radiation. Those particles that are emitted is the radiation. And if the radiation is just energy, that's what we call gamma radiation. But beta particles, positrons, alpha particles are actually that have mass and could cause chain reactions of nuclear decay. And there's this whole sub genre, I guess, or topic of chemistry that is nuclear chemistry. It gets very, very detailed, but I just wanted to give you a brief, hey, radioactivity, nuclear radiation, these nuclear reactions exist, and they do affect the nucleus, whereas most chemical reactions do not.